Welcome, everyone, to another edition of This Nanup Life. I'm Peter Sprifilis, and this is my observations of what we are doing on and to the planet we all call home from my base here in Nanup, down in the southwest corner of Western Australia. If you haven't done so already, please head over to the website, thisnanuplife.net, and subscribe to receive updates about new podcast episodes and the accompanying blog posts, and leave comments. It would be great to hear from you. For today's episode, I'm going to be looking at what prior mass extinctions can tell us about where we are taking the global life fleet. Having had some feedback from some readers of the accompanying blog post, I'm not quite sure whether I should put a PG rating upon this podcast. It seems to be perhaps less uplifting than some of the podcasts I've done previously, but please try and bear with it. I think we have a lot to learn from prior mass extinctions. So let's begin. A key point about the 5 stages of grief is that we can experience them in any order. I recently oscillated between all 5 stages: denial, anger, bargaining, depression, acceptance, as another 6-day February heat wave with daily minima as high as 30 degrees and maxima topping out at 47, that's 117 Fahrenheit, rolled across the southwest. The fire risk was extreme. It was too dangerous to stay out in my hut in Nanup in this sort of really hot, dry weather with such tinder dry bush. A comfortable time of day for me to take some much needed exercise to keep my weight under control? None really, but if I set the alarm for about 4:30, I could trudge around without getting too hot and too sweaty. The energy use powering air conditioners day and night in Perth, the state of Western Australia's capital city, which has about 2.1 million people living in it, was through the roof, noting that we burn coal overnight to power those air conditioners. While this is happening, I'm recalling a conversation I had with the Bureau of Meteorology staff in the mid-1990s when I was trying to work out how weather was correlated with how people came to emergency departments. And I remember being told by a meteorologist that we used to average only 2 days above 100 degrees Fahrenheit, that's 37.8 Celsius during February, the southwest's hottest month of the year for most of the 20th century. However, this heat wave and this succession of heat waves is really just a taste of summers to come. This year's one has been brought to us by record warm ocean temperatures and what's called a mild El Nino. But to quote the Bureau, Australia's climate has warmed by 1.5 plus or minus 0.23 degrees Celsius between 1910 and 2023. Leading to an increase in the frequency of extreme heat events, such as the heat wave we've experienced just recently. So it's official. We're blowing through 1.5 degrees C as we speak, which was the target of climate action a decade or two ago. We now talk about higher limits because we know we're not going to maintain a level at 1.5. And we're not stopping. Global greenhouse gas emissions continue to increase at just over 1% per year. CO2 emissions alone topped 37 gigatons in 2023, which is a new global record. Atmospheric CO2 levels are currently 422 parts per million and are at their highest level for 14 million years, an increase of 50% above pre-industrial levels in less than 3 centuries. And it's worth noting these levels could easily double by the end of the century. Children born today will likely be living with CO2 levels similar to those when dinosaurs roamed the South Pole over 60 million years ago. So a key question that runs through my mind is, what will be the consequences? Not just for us, but for all life on Earth, given the rapidity of these climatic changes. Atmospheric greenhouse gas concentrations have been both higher and lower than now in the Earth's past. There have also been several periods during the Earth's 4.5 billion years existence where life has experienced devastating extinction events. 5 mass extinction events, where likely 75% or more of all species of life disappeared in less than a couple of million years, have occurred in the last 500 million years or so. All were associated with extremes in atmospheric greenhouse gases. So what can we glean from these events about the relationship between rapid changes in greenhouse gases, like we're doing now, to the climate and the atmosphere, and the survival of life? A good place to start is the earliest event thought to have nearly wiped out all life, the oxygen catastrophe, also known as the Great Oxidation Event. This extinction commenced about 3 billion years ago and demonstrates that our atmosphere always needs some greenhouse gases, sort of in a Goldilocks range, for life to thrive. Too little CO2 and methane, and the Earth pretty much freezes over. The catalyst of the oxygen catastrophe was primitive blue-green algae, also known as cyanobacteria, evolving chlorophyll-based photosynthesis, that is, harnessing sunlight to convert CO2 into carbon-based life molecules, such as proteins and DNA, and pumping out pure oxygen as waste. During these hellish times, the Earth's atmosphere was unbreathable, with almost no oxygen and high levels of CO2 and methane. Over the years, the cyanobacteria sucked most of the CO2 from the atmosphere and gradually pushed up the oxygen levels from near zilch to about a tenth of today's atmospheric oxygen concentration of 21%. The free oxygen rusted a lot of stuff, particularly iron dissolved in the world's oceans. That oxidized iron fell to the bottom of shallow seas and deposited the banded iron formations we mine for iron ore across the world today, including Western Australia's Pilbara region. The oxygen also reacted with atmospheric methane, which is a much more potent greenhouse gas than CO2. This meant atmospheric methane levels plummeted, which together with the falling CO2 levels created an icehouse effect, that is the opposite of a greenhouse effect. The climate became colder and colder, resulting in glaciers likely making their way all the way from the poles to the equator. It was probably the rise in atmospheric oxygen more than glacial smothering that wiped out so much life, however. Most life at the time were humble bacteria adapted to living in low oxygen environments. These are known as anaerobic bacteria. Surviving descendants cause bad breath if you don't floss properly, and make compost stink if you don't aerate it enough. However, some can still be found living as they did billions of years ago, in rare stromatolite colonies, in an uneasy harmony with oxygen-belching bacteria on the edges of warm, shallow seas, including at Shark Bay in Western Australia, about halfway up the West Australian coast. So let's move on to the Great Dying. The poster child of what happens when atmospheric CO2 levels rise, or open air quotes, rapidly, is the Great Dying, also known as the End Permian extinction event, which occurred about 250 million years ago. Less than a quarter of all known species of life across land and sea survived this event. Previously abundant corals, trilobites, early fish species, and many terrestrial tree, insect, and early reptile species were wiped out. The likely culprit was volcanic activity creating the Siberian traps. This incomprehensibly massive million-year episode of volcanism in Siberia extruded enough lava to cover the entire USA landmass a kilometre deep in fresh rock. Volcanic gas emissions and associated widespread fire on land and underground carbon fossil beds caused about a fourfold rise in atmospheric CO2 and other greenhouse gases from levels that were roughly similar to today's levels. Global temperatures rose about 8 to 10 degrees Celsius. Sea levels rose as warming oceans expanded, and ice melted on continents and was carried by rivers into the sea. At the same time, the Earth basically became glacier-free. The oceans became anoxic and experienced widespread algal blooms as ocean temperatures rose. Most extinctions occurred during the air quotes rapid rise in atmospheric greenhouse gases and temperatures. By rapid, we are talking temperature increases of no more than a degree or two every 2 or 300,000 years. Now, that is rapid when looked at from a geological timescale perspective, but rapid compared to our fossil fuel emitting climate recklessness. We've doubled atmospheric greenhouse gases and increased global temperatures 1.5 degrees in only 250 years. This is 3 orders of magnitude, 1,000 times faster than during the Great Dying. Given what we know about the relationship between greenhouse gas emissions and the Great Dying, the sheer velocity of change we are wreaking upon our atmosphere and ecosystems is breathtaking. And by that I mean likely to take the breath away permanently from many, many species of life, many of which we depend upon for our lives. There was perhaps only one mass extinction event which had a more abrupt precipitant than our 250 years of burning fossil fuels. That is, when a 10 to 15 kilometre wide asteroid smashed into the Yucatan Peninsula about 66 million years ago, bringing the age of the dinosaurs to an end, also known as the Cretaceous Tertiary extinction. Most animals larger than 25 kilograms were wiped out as the chain of life across the planet was disrupted by sudden ocean acidification and dramatic atmospheric greenhouse gas and climate changes. Ocean pH dropped about 0.2 to 0.3 units due to acid rain over as short a timescale as a few hundred years, noting that lower pH equals more acid. This was caused by the asteroid blasting vast quantities of sulfur-rich rock into the atmosphere. The sulfur combined with oxygen to form sulfur dioxide, which acidified the rain. Many shell-building plankton, also known as foraminifera, ammonites, marine and freshwater snails, and mussels could no longer build their acid-soluble calcium carbonate shells and were immediately wiped out. A complex cascading chain of ecological collapse ensued, which took several 100,000 years to restabilize. Ocean acidification and anoxia, greenhouse emissions from volcanism, and post-impact atmospheric dust and haze may have all played a role at various stages of the ecological collapse and eventual restabilization. Today's ocean pH has dropped by 0.1 units in only a couple of hundred years as the ocean has absorbed our fossil-fueled CO2 emissions. That is, we are acidifying the world's oceans at least as rapidly as after the asteroid impact. Modern shell-building plankton are already struggling to synthesize their shells, and we are on a path that will acidify the oceans more than when the dinosaurs went extinct if CO2 emissions are not rapidly reduced. That is, we're on track to wreak catastrophic damage to the world's largest ecosystems, our oceans, before the end of the century. The air quotes good news is other mass extinctions teach us that on geological timescales, the Earth has mechanisms to moderate high greenhouse gas levels. For example, algal blooms spawned by hot oceans die and sink, burying carbon under the seafloor. As mountain ranges rise as a consequence of, say, the Indian subcontinent slamming into Eurasia, the Himalayas are still growing. Newly exposed mountain range rock absorbs CO2 as it weathers, lowering atmospheric CO2 levels and cooling the planet. The problem for life on Earth today is that it takes thousands of years, not decades, for these mechanisms to appreciably lower atmospheric CO2. And clearly, our ecosystems need action now. Despite all our political masters huffing and puffing, has anyone seen a realistic plan to lower global emissions at all? The measurements at Mauna Loa in Hawaii show there isn't one in action yet. Atmospheric greenhouse gas concentrations are tracking relentlessly higher. Anyone who thinks that the rate at which we are emitting greenhouse gases and acidifying our oceans is okay is kidding themselves. As we continue to heat the planet, acidify the oceans, and destroy wilderness, we are losing species at least 100 times and perhaps as rapidly as 1,000 times faster than before industrialization. That is, a human-induced sixth mass extinction is underway. In the absence of genuine climate action, we risk annihilating most life on Earth more rapidly than any prior mass extinction. It's just impossible to overstate how risky it is to continue our business as usual fossil-fueled ecocide. When billionaires start to spend less on bunkers and more on global cooling experiments, we should take notice. Even they are working out there is no point having a bunker if there is no food or folk, that is, an ecosystem to service it. So apologies, and as I warned, this has ended up much darker than I intended when I started researching this topic. But rather than return to the 5 stages of grief I began with, perhaps I could scratch out a note of optimism in Chernobyl. Chernobyl, where humans just don't go much anymore, gives a hint of Gaia's powers of recovery, even when we make catastrophic mistakes, if we just leave an area alone for a while to recover from our vandalism. Until next time, thank you for listening.